Welcome to the Horticulture Seminar Series. It is our pleasure to welcome Dr. Chris Watkins as our speaker today. Dr. Watkins is Associate Dean in the College of Agriculture and Life Sciences and Director in Cornell Cooperative Extension at Cornell University. He carries out a research program on storage and ripening of fruits and vegetables from both applied and fundamental aspects. His primary interests are in understanding the underlying mechanism of fruit responses to post-harvest technologies and relation to pre-harvest factors. He has published over 176 peer-reviewed papers, 18 book chapters, 44 conference proceedings, and 126 trade newsletter and technical articles. Dr. Watkins has graduated 9 MS and 12 PhD students and hosted many visiting scholars as well. He was awarded with the Winston Churchill Memorial Trust Fellowship, ASHS Outstanding Extension Educator Award in 2005, and CAL's Outstanding Faculty Award in 2018. He was elected Fellow of ASHS in 2015 and Fellow of the International Society for Horticultural Science in 2021. In addition, he was an invited speaker of the B.Y. Morrison Lecture in 2016. He is past chair of the ISHS Division for Post-Harvest Physiology and Quality Assurance, as well as editor-in-chief of the journal Post-Harvest Biology and Technology. With that, the stage is all yours.
So much for the introduction. It's all live.
You're welcome. Oops, sorry. I have the microphone, sorry.
Now you tell me. All right, thank you. Can you hear me all right at the back? I normally don't need a microphone, but I have a voice that carries. So thank you for the invitation, Bimu. Thank you to the department for inviting me here. It's an honor, of course, and it's my first time to Texas A&M. I can't believe I've almost gone through an entire career without being here before. So what I'm going to do today is talk not about apples. So, well, let me just start by sort of talking about maybe what I do, and then tell you that I'm not going to talk about it. All right. So my program is based on maintenance of quality, especially new cultivars. We're talking at lunch. Many of you will be aware of the Honeycrisp apple. That apple is God's gift to post-harvest physiologists, because there's not an apple on earth that has more physiological problems. I'm going to show a few of those in a moment. And the beauty is that it's being used in all the breeding programs as well. So I think you had Kate Evans a couple of weeks ago, Cosmic Crisp. They used to claim that their apple had no problems. They don't claim that anymore. But Wild Twist, Evercrisp, many of these new varieties have Honeycrisp progeny, and are keeping me busy for the rest of my career trying to solve those problems. Talk about careers, I've been very fortunate to be on the 1-MCP or 1-methylcyclopropene bandwagon. I first started working with it in 1999, before some of you were born, when a chemical company came to Cornell and asked me to do some test trials. They were trying to decide whether they wanted to buy the patent. And I'll talk a little bit more about 1-MCP, but we did this work and we thought it was like voodoo. It didn't make any sense whatsoever, but we saw the results. And then the company that we were doing the work for missed on getting the patent by 12 hours. And Roman Haas, who I will also mention, basically have made many millions of dollars as a result of that decision. A lot of work also on dynamic controlled atmosphere storage, which I'm not going to talk about today, but basically is how you can measure using technology the stress on apple fruit as you lower the oxygen and then adjust the oxygen level in the storage. So whereas traditionally we would use about 2% oxygen in apple storages, and other fruits, we can now go down to levels of 0.5 and even lower safely, because we are measuring the stress of the apple either by fluorescence or by respiratory quotient or by ethanol. So that's been really exciting as well. And then physiological disorders has been what basically, because of Honeycrisp, most of my work, and then we've also been looking at the effect, of course, of post-harvest on nutritional status, and then lately extending our work to the microbiome. So what I'm not going to talk about today is flesh browning. These are all apples you don't want to eat. That right-hand bottom is a thing called stem end flesh browning. It is a major problem of Gala apples, huge limitation. Honeycrisp, I just mentioned. These are all things that hopefully you don't see in the marketplace, but because a tremendous amount of fruit is being lost before it gets to the consumer. This doesn't want to, oh, okay. So, all right, well, you don't want to see more photos really, but I just want to make you happy that I'm not going to spend this whole conversation talking about browning, which I could do if I had the chance. What I thought I wanted to do today was talk about something that is related to the whole issue of technologies. I've had a great day visiting lots of people, and I use the word curmudgeon, and it was not a word that's used very often, but I am getting to the point in my career where I am becoming a little bit of a curmudgeon, a little bit cynical, and I hope that won't come through too strongly, but I sort of want to talk about what's going on with technologies and think about the reasons that, we have many technologies, but they don't always reach their full potential, or they don't reach their potential at all. So what I'm going to do today is talk about three things, just an overview of the available technologies. And I put in parentheses and treatments because one of my engineering friends, a colleague of ours, Bart Nicolai in Belgium, is an engineer and therefore very precise. And he said, well, no, these are not all technologies. These are also treatments. So I'm going to use those terms interchangeably. What I'm going to then do is I'm taking three examples. One MCP, which I've already talked about, but you may not all be familiar with, nitric oxide and skin coatings, just to illustrate some of the contrasts about the technologies, and then finish up with some comments about the factors that affect the adoption of technology that are much more than their availability. So the first part is, of course, I have to pay homage in the post-harvest world to the number one technology, number two technology, number three technology is temperature control, the cold chain. So, and I'm not going to read through that list, but essentially we know that just managing cold chain is the most important thing that we can do to manage quality of horticultural products. If we look at the range of technologies that are available, you'll see that there's a large number of them. The green ones are the ones that are used routinely, even though I'm going to highlight some of the barriers to those usage. Ozone is also, again, depending on the industry. The red ones are technologies that are either being used for very specific needs, like irradiation is being used for market access, for example, from Hawaii into the mainland of the US, sulfur dioxide for table grapes, heat treatments. Tremendous amount of research has been published on heat treatments, but actually very, very limited commercial utilization. And I could have done another section on heat treatments, which you'll be pleased that I didn't. And then there's a whole range of other technologies that are being either in use or are close to being available to the industries. And we're in a period where there's a tremendous amount of interest in post-harvest technologies. First of all, fruit loss and fruit waste. About 30% of our production in fruits and vegetables is lost after harvest. And in terms of the the United Nations goal of reducing food waste by 50% by the year of 2030. That has become part of the mantra. It's also become part of the mantra of venture capital funding, which I'm going to convince you in my curmudgeon mold has had quite a distorting influence on some of the investment decisions that are being made. We have an interesting dichotomy between local and large-scale agribusiness. So whilst we are working a lot with large-scale agribusiness, we have a lot of focus on local foods, locally sourced food. And one of the interesting stories there is a CoolBot system. CoolBot is basically you take an air conditioner, overwrite the control of the air conditioner so that you can, as a small scale farmer, for $300, you can have a cooling room as opposed to a very expensive refrigeration unit. The interesting thing about the CoolBot, and I wish I had a photo of it there, of course, right now, is that it was developed by a New York person for the developing world. So called, and then it has now come back to New York. We have a lot of our farmers that are using the CoolBot as a cheap way of maintaining the cold chain. And then, of course, organic minimizing of chemicals is another driver, microbial and chemical contamination, especially food safety as it relates to the Food Safety Act FSMA. Plastics, we'll touch on this, you know, the abhorrence about plastic, which may or may not be valid. And a lot of niche products, so we're getting away from the one size fits all to specific type technologies that, for example, in the UK, there are special pads that are used for strawberry ethylene absorbers, which theoretically should not affect strawberries because they're non-climateric, but they do. The issue of food miles is front and center. I know Cornell students are very focused on it. I don't know about whether that's the same in Texas, but and lastly, worker health and safety is a huge component. So a lot of this is driven by consumer perceptions and desires. So I'm now going to move to the second part, which is examples. So for those of you that aren't familiar with 1-methylcyclopropene or 1-MCP, this is the chemical that I told you I was in at the early stages. It's been a very exciting journey. Very simplistic cartoon on the right-hand side that basically says that 1-MCP competes for the binding site for ethylene, and therefore, if 1-MCP has taken that location on the binding site, there's no room for ethylene, and therefore you get no ripening senescence. Gross oversimplification, but I just wanted to sort of lay it out there sort of simplistically. It was patented in 1996 by Ed Sisler and Sylvia Blankenship in North Carolina University. And Sylvia will tell you it sat on the desk. No one seemed to be interested for through a few years until a company came along known as Floralife in 1999. And the owner of that company, John Daly, came up with a very simple technology of encapsulating the 1-MCP inside of cyclodextrin. So essentially sugar. So white powder, you add water, the 1-MCP is released. There's no chemical development of the 1-MCP. So it was used for floriculture, and then Roman Haas, the people that missed out, no, that got it instead of the company that I was doing the experiments with, did buy the patent and went through the registration process. So it was registered in the USA in 2002, in Europe about 2005, but that's another story. So no, we're in a period in history where chemicals are generally not regarded as very fashionable. and often the opportunity for registration is very difficult. But 1-MCP really went through the regulatory system with a remarkable ease. Number of reasons is very targeted mode of action, given especially because humans do not have ethylene receptors. A very good safety profile. So there was no evidence to be done through the normal animal studies and so forth that showed a problem. The concentrations that are applied, 1 part per million or lower, are very low. Short treatment periods, typically just commercially like a 24-hour period, but actually it can often be a lot shorter than that, and no residue. So in fact, it's a frustration by the regulatory agents because you can't measure 1-MCP in the fruit. So there's no way of telling for sure that a fruit has been, or a vegetable, has been treated with 1-MCP. The second that contributed to its success was a very easy to apply release system. As I mentioned, you essentially add water and the compound is released into the atmosphere. Third, and this is actually pretty important, although maybe the same is true for citrus in this part of the country, but basically if you have a technology that you can apply to apples, given its international value, you have a cash cow, so to speak. So the fact that this 1-MCP was so successful with apple fruit meant that it was taken up widely internationally. The other interesting thing was because of the fact it was powder and easily available, it was made freely available to scientists all over the world. So Roman Haas were very clever in that sense because they've got an incredible amount of free research. So and I will show you in a moment just what that has meant to the scientific community because there were so many small scale experiments to be done. So you can find out all the pluses and minuses for every product. But the most important thing that I think, and I'm going to come back to this, is the patent control. And I will contrast that with nitric oxide in a little while. The fact that you have a patent and that control of that patent allows you to go through that, well, justifies the incredible expense of millions and millions of dollars that you have to go through in order to go through the regulatory process that I talked about. So a large literature approaching about 2000, that this is peer reviewed, not Acta Horticulturae, but 34 climateric fruit and fruit vegetables, 17 non-climateric fruit. In theory, we would think non-climateric fruit does not involve the action of ethylene, but actually 1-MCP has shown us that it can and does. 31 vegetables, fungi, and the work keeps on going. All the basic work has happened. What's frustrating now, we're in an era where everybody is applying 1-MCP with something else. So, oh, I've got 1-MCP and a product, chemical B, and it just goes on and on, but hopefully we're getting to the end of that. So why was the apple the poster child? It's essentially because when you buy an apple, whether it is at the time of harvest or after long-term storage, the ideal apple is the one that tastes very much like it is at harvest. In other words, by stopping the ripening process, you end up with a high quality texture apple. And if someone may ask, well, what about the aroma? That's also an interesting story because yes, 1-MCP does suppress the aroma because ethylene is involved in a lot of aroma production. But all the taste panel work that has been done shows actually consumers prefer 1-MCP treated apples to non-treated because a lot of the aromas that we associate with apples are over-ripening aromas, the esters. So actually you end up with an apple that is more like the time that it comes off the tree. High volume fruit with existing controlled atmosphere, storage infrastructure. So the infrastructure existed around the world. And then this disorder is a disorder known as superficial scald. We've had some great, we've talked about the metabolism that's associated with this disorder, but the bottom line is if you treat the fruit with 1-MCP, you inhibit ethylene, and that inhibits the compound associated with superficial scald development. And as a result of the effect of 1-MCP, it gave Europe the green light to ban the chemical diphenhylamine, which is an antioxidant that's used on a lot of our apples that we still use in North America, but is not allowed anywhere else in the world. The original delivery system, as I already indicated, pretty straightforward. Essentially, you take off the top of the lid, you pour in the solution, you push a little button, which gets the fan going, and then 1-MCP is distributed inside of the storage room. This is now obsolete, but that was the original technology that was used. However, it has been a much more difficult proposition with other fruits. Pear fruit, as Amit is back there, has a technology to overcome the effect of 1-MCP on pear fruit. But the bottom line is that if you treat 1-MCP, treat pears with the 1-MCP, you can have hard and firm pears for a couple of years, right? Yeah, no one's ever going to want to eat them, but you've got lovely looking pears. But many of these other fruits, avocado, banana, pear, tomatoes, they have a ripening process post-harvest, softening that make them desirable for us as consumers. And the balance between delaying and inhibiting ripening is very, very difficult. It also brings in pre-harvest factors, where if each of you had an orchard block, some of your fruit is going to respond differently depending on what your orchard block produced, for reasons that we don't necessarily understand. And just to give you an example of how things can get messed up, this is mature green tomatoes stored at 12 degrees for either 9 days or 18 days, untreated or with 1-MCP. And on the right-hand side, you see the very undesirable commercial treatment of 1-MCP, where some of the fruit remains green and perhaps will never ripen, and the others have ripened a little. So that variation from a commercial perspective is unacceptable. It's better to have all, even if it's less desirable, it's better to have uniform less desirable than a mixture. Then we're into the world of how do you move beyond the technology and integrate it into the handling system. We're talking a lot at lunchtime about bananas. And no, at least in the US, we have a very vertically integrated banana system. It's shipped in, it's harvested 2/3 green, shipped in, goes to distribution centers, and treated with ethylene, goes to the supermarkets, and it's sold. What AgroFresh spent a lot of time, effort, and money was on a ripe lock system, where you could, it's basically a modified atmosphere package with 1-MCP. And what that showed is that, or what that demonstrated is that you cannot introduce a technology easily into a pre-existing handling system that is so vertically integrated and tightly controlled. And so that was sort of a take-home message to all of us, and I believe they've given up on ripe lock and it's no longer available. But if any of you like to have fun on the web, go in and look at the video on the ripe lock. It's kind of fun. With vegetables, limitation for 1-MCP on vegetables is many of those benefits of 1-MCP are apparent only after you have abusive conditions. For example, ethylene contamination, when the product is being shipped, say, from Texas to New York, all right, when you've mixed loads, but it doesn't happen enough to warrant the cost of applying 1-MCP in the first place. And most of the experiments that have been done with vegetables have shown results by co-applying ethylene. which you don't normally have in a real life situations. So the abusive conditions are not predictable, and therefore the economy, the economic factors just don't help. So the result is there's very minimal use on vegetables, even though there are potential advantages. But it's kind of interesting how things can change. And this is the best example of how cost-benefit ratios can change. So the Food Safety Modernization Act in the US has had a tremendous impact on horticultural industries meeting the requirements. And part of that, as I mentioned earlier, is the focus on worker safety and environmental issues. So you may or may not be aware that broccoli, say out of California, is they're put into these very heavy waxed cartons, and ice slurry is poured on top of the cartons, and then they're shipped across the country. And you can be in a supermarket sometimes, and there's a wet box on the floor, the ice is melted as they're loading the broccoli onto the shelves. Well, 1-MCP, and that work on the top, which you can't see, but there's a less green and a dark green, work from a colleague of ours, Randy Beaudry, in Michigan State, showed how well it can work, but it wasn't being used. But 1-MCP eliminates the use of potable water required for icing, reduces hazards, wet floors, it reduces the need for those very heavy waxed cartons, and it reduces the shipping costs because 44% of every 18-kilogram box of broccoli is ice. So economically, if you can get rid of, have less resistant cartons, you're not having to use ice, there's a huge money saver there. So that's an ongoing change that's taken place in the industry. So sort of summarizing the effects of 1-MCP on all horticultural crops. Number one is the issue of delay versus inhibition of ripening. The second is the cost of the technology relative to the product response. The incorporation of the technology into handling, storage, and transport systems, as in the banana situation. The scale of the industry doesn't make sense if you're a small operation to be worrying about applying this technology. Competition in the marketplace, that was actually huge. Early on in New York, and I think across the country, supermarkets actually within a year were demanding that you had to have used 1-MCP or they weren't going to buy your apples. So that meant if you were resistant to buying 1-MCP or using 1-MCP, you lost your market share. So another factor. And then the last comment here is that market access. So if you can use 1-MCP and allows you to buy ship, as opposed to using planes, you have a huge cost saving as well. But as a commercial product in transition, AgroFresh became public. It is now a private company because its shares were so undervalued that one of these companies that picks up undervalued companies bought every share available. So it's a whole different world for AgroFresh. 1-MCP is off patent, and in some other countries came off patent in 2014. So there are many new players and drivers, and again, the venture capital food waste group jumping on this. There's also different application methods. Early on, we were absolutely obsessed with having sealed rooms, tight, minimal gas exchange, and now we know you do aqueous treatments. Not that is registered yet, but incorporation of polymeric films, packaging, paper packaging, and sachets. So these all provide flexibility when sealed rooms are not available, and ability to apply lower concentrations. I think strategically, AgroFresh made maybe not from the cost of counter point of view, but made a strategic mistake in focusing just on high volume products like apple and ignoring everything else. So they've really left a vacuum. There's been other providers of 1-MCP, especially in China, for a long time. The other factor about 1-MCP, it used to have a list of registered products. And in some places, you may or may just look at that and just see there's a lot of crops, a lot of fruits, a lot of vegetables, a lot of flowers, and everything and so on. And basically saying you can use 1-MCP on anything that you like, even though we know it has no particular value, but it doesn't seem to bother. That's my curmudgeonly statement. And then Hazel Technology is a big competitor in the market, where they just simply throw sachets on top of the bins and claim some pretty remarkable responses. And the last technology that sort of, or commercialized process that is being commercialized right now is a harvest hold, which is basically a plastic film with 1-MCP incorporated, and then you just simply lay those sheets of paper over the fruit. So I just want to move now to a contrast, and that's nitric oxide. And I'm going to use this as an example where I think, even though there's some incredible responses to nitric oxide, I'm editor of a journal called Postharvest Biology and Technology, and we get papers all the time on nitric oxide, claiming that it's going to be the greatest thing on every product. I think there is a limit to the way it can be commercialized, and because of the patent, which I will come back to. So even if it's effective, what is this commercial use? For those of you that aren't familiar with nitric oxide, you can apply as a gas, the same way that you apply ethylene to bananas, or you can apply donors of NO, SMP, sodium nitroprusside, and ditano. I'm not even going to try and say that name in full. And there's a large literature that exists. Now, basically, it has it's a powerful way potentially of controlling many aspects of ripening and senescence. But what is the potential use for what is the potential for commercial use of nitric oxide? Well, on one hand, it is naturally occurring. So toxicity and handling issues are analogous to ethylene. So as I said, you can apply nitric oxide the same way that we apply ethylene. Nitric oxide gas application would require gas-type fumigation chambers, monitoring of atmospheric discharges, although it could be applied as a donor. But there are significant regulatory concerns, and because plants and animals do not have identical pathways for nitric oxide metabolism, and nitrate reductase convert, spanning their error there, sorry, nitrate to nitrite, which has the potential to be converted into nitrosamines. So the barriers are a lack of standardized treatment protocols, and there's a post-harvest biology and technology. Last year, there was a very excellent review that highlighted the limitations of nitric oxide. But most important is there's no regulatory approval that currently exists for the use of nitric oxide. And so my question, and a very valid question that no one wants to address when they're doing the work, is who will pay for the commercialization? Because if you don't have any patent control, then why would you make the investment, which is literally I don't know what, do you have an idea? I think it's like $10 million to register a new chemical. Does that sound about right? It's a pretty massive amount of money. Yes? No? Good enough. 10 million. All right. Well, since COVID, maybe 12. So my third example, and I think I'm doing okay for time, is edible coatings. And I look at that in the context of plastic films. So if we think about plastic films, and there are some countries in the world that have already banned plastic films, but they actually have a very critical role. product identification and storage instructions, protection from physical damage, including farm consumers, extending shelf life by creating high humidity conditions that reduce weight loss and shrinkage. They maintain fruit safety, protection from contamination. And actually, it's very interesting in the apple world. I don't know whether it's starting to return, but during COVID, the whole market shifted away from open source apples in the supermarket to apples in bags, because people inherently felt it was safer to have those apples in bags rather than people picking it up with their COVID-ridden hands. And then you have the advantage of extension of shelf life from modified atmosphere storage. And in fact, in the case of modified atmosphere packaging, we would not have a fresh cut industry if we did not have the availability of plastic films. However, packaging or plastic packaging is considered evil. And just some quotes, plastic packaging wreaks havoc on our planet. Even though plastic packaging plays a vital role in protecting food, more sustainable solutions are needed. United States produces almost 36 million tons of plastic waste. 60% of all the plastics ever produced are currently sitting in landfills or in the natural environment. And the reality is that the use of plastics, the proportion of plastics that is used for fresh produce is likely very small, but is part of the mantra of the venture capitalists. Oh, just one other comment before sort of questioning the anti-plastic. And actually, I'm pretty neutral about this, but I want to do a little bit of a defense of plastics. So this group in England talk about the trade-off that removing plastic packaging from fruits and vegetables is going to result in shorter shelf life and therefore greater increase in fruit waste. The fresh produce is estimated to be the most highly wasted type of food in the UK. This study was a UK study. And it's likely that fruit waste has a greater environmental impact than the production and disposal of plastic. But last and most importantly, to my knowledge still, there have been no full life cycle analysis that has actually compared edible films, which I will talk about in a moment, and coatings, and the versus packaging. So we don't know whether the effect of these on the environment compared to plastic is we don't know whether it is real, and we don't know whether it is better or worse. So with that little preamble, let's move to edible coatings. These are very thin layers of edible material applied to surfaces. They can be polysaccharides, proteins, lipids, and composites. And they have been around for a long time, which you would not get the impression from the venture capital world. They've had a long history of use in apples and citrus. Do they use waxes in? Yeah, okay, in Texas and there are three main types of wax, which again I won't go through in any detail, because each of these also have some interesting side stories about, for example, what is kosher and what is not kosher. So what waxes you can eat can be affected by your religion. And then there's been other skin coatings around for a long time. Semperfresh. I worked on Semperfresh at a date that I don't want to tell you because it will age me. And then just about every fresh cut product that you eat has some sort of coating, edible coating to help protect that product, especially apples to prevent the oxidation and browning. But it's a very highly topical area. Cladribine, and I'm sorry that this figure only applies to 2017, but the bottom line is tremendous explosion in research. And then there are many new players, Mori and Appeal. I'm going to just talk about those two in some detail. So Maury is a company that bought the patent from a MIT group where they looked at the show very good responses with bananas and strawberries. I will come back to my pet peeve about strawberries in a moment. I just check, is anybody doing work on coating of strawberries here? You are? Oh, I may offend you in a moment. Are you working on strawberries? Oh, okay, good. Then we can still be friends. You're not going to hate me because I am going to tell you my pet peeve in a moment. And so this is what is going on in this world. Maury, they're putting awards. They have 50 million in Series B1 funding for commercialization and 16 million in Series B funding. And that's probably a year old, but money is pouring into this technology. The research person in the company actually is a Cornell graduate, and she was telling me, we were talking the other day, she's working, they're looking at using it for lettuce, minimally processed lettuce. And then Appeal is just an amazing story. Appeal, and this is an example from their website. Appeal for avocado is a proven way to achieve heartier avocados, blah, 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 blah. But by August 18, 2021, they had their valuation was $2 billion. They had, they raised an additional $250 million. And the Fruit Logistica in Berlin last year, they talked about the 42 million pieces of fruit that were presented from waste. They were expanding into imaging and connection with produce databases, because I think they're starting to realize that there isn't as much potential as they thought there was, and they're actually starting to lay people off. But the frustrating thing for us as post-harvest scientists is there's no independent validation. They wouldn't allow that product to be tested by university. I'm not saying we're the be-all and end-all, but it's frustrating where you're being asked by your industry about should they use it, and you can't give them a quick response. Okay, here we do my little curmudgeon bit about strawberries. This is from Appeal. The coatings are made of, but I hadn't mentioned, Appeal is using waste product, discarded skin coating, to be used as the coating. So the coatings are made from molecules of discarded materials from organic produce, anything from pear stems to leftover grape skins, from wine fermentation to grass clippings. And here's my pet peeve. Strawberry, great research tool. So if I see a paper where somebody says, we want to use strawberry as a test product for a test for testing the technology, I'm all for that. But the reality is, the idea of putting a coating on a strawberry is absurd, because it is harvested in the field, it goes into packaging, it gets treated with high carbon dioxide, and it gets shipped. There's no way that you can treat with a skin coating. One of the Driscoll's reps told me they came to their farm and said, well, couldn't you spray it on in the field? And they had to explain to them very gently that no, skin coatings don't move magically around a fruit. So, and then you have all these sort of statements about urgency and so forth. But here's the real reality. The best skin coating for strawberries is yum. So those are just 3 examples with some interesting contrasts. I could have talked about DCA, I could have talked about heat treatments, but you're lucky I don't have time. So I'm going to finish off with some factors that affect the adoption of technologies that I think we all need to keep in mind. So first of all, the scaling up from laboratory to commercial reality. Every new technology and development of existing ones has to be viewed through the lens of 1, efficacy, the performance of an intervention under ideal and controlled circumstances, i.e. what you do in the lab, right? Second is the effectiveness. So the performance of that intervention under real world conditions, which is hugely different. So, coming back to my strawberry example, when we do that, you're likely to do it in the lab, using sterile conditions. If you've got a drench of any sort and you're then applying that stuff for the third or fourth time go around, it's not going to work. The economics, the return on investment, and then environmental sustainability, which is important and is in people's minds, whether that be food miles, food safety, or worker health and safety. Just to give you an example of how things can be sound really good, but experimentally, but not in the real world. This is a quote from a colleague of mine that I can't actually tell you the company, but they did a test of a new technology in California, and it took 1.5 seconds per box to introduce this technology, which to me sounds like nothing, right? But by the time you multiply that up by thousands and thousands of boxes, it was economically unsustainable. So it just illustrates how I think, I'll speak for myself. I'm not always good at imagining all the real life scenarios and plus, industries will do things you can't even imagine they will do. Okay, in conclusion, expanding and expanding a diverse range of technologies are available. There's no one size fits all. There's increasing differentiation between validated and available technologies. There was a time, and we will never go back to this, when the universities would do research and then it went to market. Very often we have co-development. So the industry is working with the technology at the same time that we're trying to catch up with what that technology can do. And there's no magic bullet despite claims on the web. So the availability of any technology is based on factors beyond its effectiveness, relative response of the product, the return on investment, does it warrant the cost, the type of industry and its scale, whether it's a commodity or a niche market. So if a niche market, you can apply an expensive technology and it will still make economic sense, where it might not for a commodity. The ease of use and how the technology fits in with existing handling practices. Regulatory hurdles. Oh, that was clever of me. Back up. Does it provide access to markets, new or existing? And the comment that I made about patent control is more and more critical, especially if it involves the regulatory aspects. Consumer acceptance. By the way, most people, if you do surveys, they ask whether you want waxed apples or unwaxed apples. They will always tell you unwaxed apples, and then they will go and buy waxed apples. And then last but maybe not least is the key decision makers in respective industries. I learned very early on in my career that a key decision maker in an industry can make a huge difference as to whether a technology will be acceptable or not. So they're the people you have to talk to. And I have my own view about post-harvest innovative treatments, whether it's right or wrong, that I think post-harvest wet treatments have little future. I think because of food safety issues, I worry about, for example, coming back to appeal, there are countries, I've been in many countries where there isn't enough water, potable safe water for the population. And they're talking about using that water to put a coating on a product. Makes no sense to me. Then we do have consumer issues about certain coatings, even though they're not always valid, and I think the future is pre-harvest defense responsibilities. Think about what we do pre-harvest, post-harvest gas treatments, physical treatments that are scaled for the specific marketplace. And I can't walk away from this without highlighting the importance of working with the breeders. And we're talking about that this morning in terms of what you're doing with the breeders, with melons, etc., but tomatoes, and then pre-harvest factors. so much of what goes on in management of the product has a huge impact on how well a post-harvest technology can be applied. And so we have to be really looking about what I think the intersections between post-harvest physiology, post-harvest pathology. The pathologists ignore the physiologists. The physiologists ignore the pathologists. I hate it when disease is in my experiments. It's just a pain and it messes up my numbers. And then plant breeders and field scientists. So just lots of being fortunate over the years that there's current and past students and technicians. I have some wonderful colleagues, faculty that I work with. One most recently, Jenny Balniffen, as I'm entering the microbiome world. She's a soil microbiome specialist, and I'm learning a lot about microbiomes vicariously through a student that's working with the two of us. So I will stop there. I apologize, I've gone over time, but we'll open up for questions. Wow. Oh, I knew I could count on you.
That's why I said we'll take questions from students first.
Oh, yeah.
I'm just trying to see paying attention.
I-
Yeah, good.
Oh, boy. I thought I was being provocative. So I think you're partly true, right, in the way that post-harvest has to reconfigure. So even though I'm cynical about the way food loss and food waste is used to justify doing stuff, it is how we should be thinking about how we present ourselves. I'm an administrator, so I can make fun of administrators. Surely you've got all the answers for apples by now. You've been working on it for 80 years, right? I mean, that's how they see it. I look at every new variety that we have as a new fruit. So we do have a role. I don't believe our golden years are over, but I think there was a little bit of a circling going on. I don't know whether you'd like to comment, but I would argue from the developing world point of view, the real need is for basic technology, refrigeration, for example. I mean, would you agree? Yeah, it's not all the add-ons that are necessary. The add-ons now come from investments in companies that are going to export fruit to the so-called developed world. So the answer is we've got life in us yet. Yeah.
Say you were to spray it on fruits and vegetables, even a day after you don't have any.
No, I think no, you can't. And so, even using radioactivity, I think they did some trials where they were able to find some activity, but I've never seen a published paper on that. So first of all, so of that 1 part per million, so using Apple example, the majority, a proportion of it is absorbed immediately into the tissue and binds to the tissue. And the rest is just goes into the atmosphere and is destroyed the minute it is in sunlight. So you can apply 1 MCP in sunlight and still get results. It's so volatile. That said, it's weird. I left that bit out. We actually we can spray Havista in the field. So using a spray tanks is commercially, and it's so bizarre because we spent all this time thinking that you had to be always sealed. But no, that was a rambling answer to your question. And no, you cannot find residues. Yep. Yep. Yeah.
Chris, I have a question if you could take one.
Oh, hang on. Go ahead, back line, buddy.
Oh.
No, I'm not taking it from the. Where's the screen? I can't see it.
They can see you in.
Oh, okay. All right.
Given the potential for tremendous advancements to be made using GMO and or gene editing technology, what do you think we can do to advance the genetic technologies into the marketplace a little more quickly?
Good question, and again, no easy answer. But one of the first GMO products produced for post-harvest was the flavor saver. Have you heard of the flavor saver tomato?
Yeah, as a matter of fact,
one of the big problems was they chose a tomato that didn't have any flavor to save. So that was not a strategic move.
I actually brought some of those flavor saver tomatoes into my class when I was teaching an honors course, and that was, I think there were a lot of mistakes made in that process, and part of the mistakes they made was in not being able to adapt their solution to the existing marketing chain, the marketing channel. They just made a lot of misassumptions.
And I think, correct me if I'm wrong, it was also done at a time of intense scrutiny about GMOs.
It was, yes.
So there are a number of factors. I think the industries are spared. Now we do have a GMO apple called the art apple that came out of Canada. Yeah, and so it's a non-browning apple. The industry is very nervous about that because all of a sudden you move from a situation of being able to say there are no GMO apples to not being able to say that anymore. But there's, I'm personally, I have no trouble with GMOs. I know that there's varying opinions on that, but the reality comes back to the comment about consumers. It's all about consumers. But by the way, who was that asked? Oh, hi. Oh, hi. Hello.
Hi, Chris.
Haven't seen you for a long time.
Absolutely.
A dosage effect? Yeah, it's very. I've got to be careful. You might know more about this stuff than I know. It depends on the product. So, for example, the pear, right? Come back to the 2-year pear. If you can apply 25 parts per billion, you're going to have a delay and a ripening, right? But what you can't do is apply 25 parts per billion in a storage room accurately. So the same might be true. Now, do you know if is he using the stuff that we gave? Yeah, but you have to make up the powder and then, yeah. I don't know. I mean, again, I'm being a little bit coy because I'm coming from the apple world. Most apples are saturated by relatively low amounts of 1-MCP, so you don't get a dose response. That said, I'm now going to contradict myself. One of the reasons I was able to get funding from the industry for MCP work years ago was I took a Macintosh apple to a review meeting and said, when was this harvested? And they said, it was in November. And they said, oh, September, blah, blah, blah. And I said, no, actually, it was the year earlier. But I had applied 50 parts per million. It doesn't make sense because the way MCP is meant to work is it absorbs to the membrane receptors. So why why is it that you've got a saturated system and you still get the advantage of this? Maybe we might get residues then. I don't know. I mean, I haven't got my head around that, the rationale for that, other than to say we don't understand exactly how MCP works. Yeah, but I would love to talk to this the Mellon person. Yeah. Yep. Yeah, a happy baseball. Yeah. Oh, yeah. I'm embarrassed to have shown that with you in the audience. We don't fully understand. You're absolutely right, and no one's going to pay you to understand it. Well, I think it does work effectively with everything else. It works too well, yeah, because Apple is really the you use the cliche, the poster child, where an apple in June of its life, the one that was harvested in September, is pretty good from a consumer point of view, because the number one criteria for consumer acceptance is texture, right? But it does work well with tomatoes if you want to keep it mature green for a long, long time. And then, but even then, I'm being a little bit sort of trite, because even within apple cultivars, there's variation. So Macintosh, which hopefully none of you, I know a couple of you have eaten it because I made fun of it earlier, the apple that I had to like until I got tenure. And then I could pretend, I could be honest and say to the people, no, actually, I think it's a crappy apple. That's like a sports car. It's a high revving, high metabolism, as opposed to a Fuji or a Granny Smith. So a Macintosh will recover from one MCP treatment, whereas a Fuji will not, I think. So even within the Apple world, we don't fully understand. But the whole area of ethylene receptors is very complicated and hard to work on. I mean, our friend Jim Giovannoni has done a lot of that work with a model system, but with apples,
Any other questions?
Yeah. Yeah, good question. So the question, in case you didn't hear, what about the role of MCP evidence for reducing fruit loss from decay? And if you think about the old classic host disease environment, then maintaining that product in a less ripened stage is going to provide resistance. However, ethylene has a lot of roles in plant disease infection. And there are examples in the literature where 1-MCP has enhanced decay in some products. In strawberry, there's a certain range where you apply 1-MCP, certain concentration range where you will have slight benefits. And then above that, you will have increased decay because you're inhibiting and the thought is that you're inhibiting phenol metabolism, which is in part responsible for disease resistance. So again, very complicated. Well, yep.
Here any reversal effect food with 1-MCP and after some time it gets rewritten. The ripening will start. This will prevent all.
It depends on the product. And so it's kind of like the Macintosh versus the Fuji. With the Macintosh, you cannot suppress it. And then we actually have some apple cultivars, Honeycrisp babies. There's one called Evercrisp. If you give Evercrisp 1 MCP, it's like giving it the kiss of death. It will immediately get brown core. Don't ask me why, but so again, variation. Every apple cultivar we're looking at and finding different ways. And luckily enough, when we started with this, it was the classic days of Red Delicious, Granny Smith, Macintosh, Empire, Golden Delicious, and all of those love MCP. And now we have a new generation of apples that don't necessarily love MCP.
Okay, because of the time.